Here's Clarence. Thank you.
Hi. Okay. Hi. I'm Clarence. Thanks for staying for this talk. So I just want to get a quick poll of the audience. How many of you have used machine learning before? Have played with it, like taken classes or something? Okay, that's a good number. So today I'm going to be talking about how to bypass machine learning systems. Machine learning has been in the news and in everywhere in tech over the last 2 to 5 years. I did a quick crawl of RSA and Black Hat, the expo floor. You know how companies always have to publish some snippets about what they do. And I was just looking for how many companies claim they were doing something in the area of machine learning or deep learning or data analytics to solve security problems. So this is just a particular instance of a company that claims to do like deep learning for malware detection and APT attacks. I thought it was interesting. So over the years, you can see the number of instances that companies have claimed to do machine learning in security. I think it's pretty interesting. From 2012 to 2015, there was pretty much a 6x increase. And 2016 it's a bit lower, maybe because people realize that it's not that easy. So this is a neural network. I won't spend too much time going into detail about what a neural network does or how it works exactly. You can find that online yourself. But basically, the idea is that you have a standard infrastructure consisting of input units and hidden layers and output layers and activation functions, which are each one of the small circles there. And each one of these units is connected to each other by a weight. And so when you want to find the output of a neural net, all you have to do is to check which activation functions are actually activated and in use, and then you would result the result would be this output vector called logits, and then you would basically feed it through a softmax function to get the prediction. And so neural nets are all about distributing blame. So during the training of the model, when you feed in data, when you get a wrong prediction during the training phase, you would basically go through the model in the process of backpropagation to assign blame to see which units were responsible for making this wrong decision. And so when you find the units that make the wrong decision, then you would basically reduce the amount of decision-making power that they have by decreasing their weights and biases by the appropriate amount to how much they contributed to this wrong decision. And of course, you can do this efficiently with optimization algorithms such as stochastic gradient descent, which you may have heard of in other machine learning algorithms as well. So the main focus of my presentation will be how to bypass this. If there are any questions about how this works at all, I'll be going into further detail. This is not just about bypassing deep learning system, it's also about bypassing just any general machine learning algorithm, which I will go into detail later. I have a quick demo here on how to bypass an image classification engine, which is one of the most classic deep learning problems. The thing is that there's this data set called the CIFAR10, and what this is just 60,000 images that are very small, 32 by 32 pixels, and they each belong to one of 10 classes. So I chose randomly 2 classes here, a dog and an automobile or a car. So what I have here is basically 2 kinds of images, the normal and the adversarial. And so I pre-trained a model that would recognize this properly. So if I try to evaluate what this image is, it's a dog, and you can see from the image on the right that it is a dog. But if you see here, dog at 10 also looks like a dog. It's a little bit more noisy, but it still looks like a dog to you and me. If we actually run this through the same evaluation algorithm, It says it's a ship. So that's weird, right? And so this is just a standard pre-trained model that you can download from TensorFlow. And you can see that you can generate images that trick these models that are trained using Google's own engines. They have been trained using GPUs for thousands and thousands of hours, things that I would not be able to afford on my own AWS account. Similarly, for the automobile, just to show you again, it's a car. I run the normal image, it says it's an automobile. And I run the other one, it says it's a, let's see. Okay, so you see, it looks slightly different, but it says it's a cat. So that's just some small example. We'll dive into each of these images and see exactly what is different, exactly how we're generating this later. Let's open up a Python console, and let's look into how these images are different from each other. So I'm just importing the standard libraries. I'm going to read in the normal dog image. It's just going to be a 32 by 32 by 3 vector because there's RGB values. So you can see it's nothing unexpected. You see the shape is 32 by 32 by 3. And the minimum value is 0 and the maximum value is 255 as expected. So the values for RGB range from 0 to 255. Okay. So what we're going to do now is to read in the adversarial image. So I want to read in the adversarial image, and okay, so this is what adversarial image looked like. We're going to take the diff of these two and see how different they are. Same shape. Okay. So the diff is just -1 to 2 pixels difference, and yet we can make the model make a wrong prediction or a wrong classification. So let's save this diff and let's see what the diff actually looks like. Okay. And the diff actually shows up here, so we can see it. It's just rubbish. It's a rubbish vector that we can add to an image to make the model make a wrong decision. Yeah. So same thing for the other one. DocF10 is another example of an adversarial image that is generated in the same method. And the difference between DocF1 and DocF10 is just how big the perturbation is. So how many pixels it differs from the original image. And the reason why we want to change the amount of perturbation between the original image and the adversarial image is because when you alter an image by 1 pixel for each color value, then it's not that easy to be detected by a human. But if you change it by, like, say, 10 pixels, then it's more possible that the human will be able to tell that something weird is going on with it. But the reason why you would change an image by a larger amount is because it's more likely for you to trick a machine learning model that something is actually different. So as you can see, the diff is much larger now, and we'll go on. So I'll go ahead and explain how these attack works and why they work. But first of all, let's look at the kinds of attack that you can have on machine learning models. In general, there are 3 kinds of attacks. You can have causative attacks and exploratory attacks. Causative attacks just means that you have access to the training stage. So in training a machine learning model, what you usually have in a supervised case is you have a bunch of input data, and you want to train the model to do something that is that you do not explicitly program rules for. And this could be the example of if you have 60,000 images of 10 classes, as you see before, then you have 600 images of each class, and you would basically train the model to recognize each one of these models and recognize their characteristics, the kinds of pixels that make up a dog and the kinds of pixels that make up a ship. And then you would basically go on to the training phase after the model is trained. After the model is trained, you go into the testing phase, and then you would feed it unseen data and see if it actually generalizes well and makes the right decisions. The exploratory phase is, the exploratory attacks are more interesting because you don't actually have to have access to the training phase. So this is applicable in most instances. Let's say you have an online Google Translate service that famously uses machine learning models to learn from its past mistakes and to make better predictions as time goes on. You don't actually have access to the training phase because most of the time when machine learning models are deployed in the wild, they don't take in general and public input in immediate training. Most of the time, you just get the results, and then the training is done separately after the data is cleaned. So you can still attack models like that by just crafting input samples that are more likely to trick these models. And then, of course, you also have the other kind of attack, which is analogous to just DDoS attacks. Basically, you're trying to decrease the reliability of these classifiers and to make them more unreliable. You want to make everything, for example, be classified as a ship, no matter what it looks like. So why can we do this? The reason that you can trick machine learning models is because they don't learn like how humans learn. And this might be surprising to many people, even those working in the field, even those who are very familiar with machine learning. When you see that a classifier successfully classifies images with a 99% accuracy, then you kind of think that these classifiers are recognizing ships and dogs and cats in the same ways that humans do. But they actually don't. So what classifiers and deep learning models do is they just look for characteristics in the pixels that happen to be common among images of the same class. And humans don't think like that. For example, when we look at a dog, even if the color of the dog were different, even if there were a large pixel differences from all examples of dogs that we've seen before in the past, we're still able to generalize well and look for certain characteristics of the image that are more high level that we're able to draw generalizations from and conclude that that is still a dog. So this is an important thing that we should take note of. No matter what we're designing classifiers for, we should make sure that the true positives are real positives, and there can be false positives in any predictions that these machine learning models make. So basically, the intuitions for how you generate examples for adversarial deep learning are you run an input model, you run an input sample through the classifier model. If you don't have access to the classifier model, let's say you were trying to do it for an online malware classifier that you don't know what model they're using, you don't know what data they use to train the model, then you just have to use a substitute model, which I will go into later. The second step is to, based on the model prediction, derive a perturbation tensor, a vector, or a matrix that maximizes the chances of misclassification. So I'll go into more detail about how to do this later. And the third step is to scale this perturbation tensor by some arbitrary magnitude. The larger magnitude you scale this by, the more chance you have of tricking the machine learning model. The smaller magnitude you tune this by, the smaller chance you have of tricking the machine learning model, but also the smaller chance that a human looking at this input will realize that something wrong is going on. So the most simple way that we can generate these adversarial images is to basically traverse the manifold and find blind spots in input. And what this means is just, let's say you have a 32 by 32 pixel matrix, and you're trying to look for misclassifications of a dog image. So what you can do is to just brute force, to change each pixel one by one, increment each value from 0 to 255, and just make small perturbations in the input to find out which image of a dog would be misclassified by this model. And this is okay. People used to do this in the past, but it would take a long time, especially if you're looking at larger images. If you're looking at malware classification, for example, then typically you have to change millions and millions of bytes, and it's just a combinatorial explosion. So to optimize this search, you can take the input of the target with respect to that target output class, which is what inspired the next method, which is linear adversarial perturbation. So if you can think of a neural network as basically a black box when you have inputs and output, and basically what you're trying to do is to feed in inputs that would result in a different output from the previous input of the same class, and then you would take the cross entropy of the input sample and the predicted class, and this can be done without the actual model as well, but you have to create a substitute model in order to get access to the inside parameters. It's easily found by backpropagation, and I have some sample code on this on a repo that I published online, and you can play with it yourself to find out how it works and to see if you can generate adversarial samples for arbitrary machine learning classifiers yourself. The last method is a little bit more complicated, and the motivation behind this method is simply to reduce the amount of perturbation that you have to add to a valid input in order to trick the machine learning model. The basic idea is that you want to try to find points in this input vector that would allow you to make small changes to the input, but then result in a larger change to the output. So this is an example saliency map, which is what we call a measure of how much each pixel actually affects the output result. As you can see in the center of the image, you actually have the largest saliency, which means that if you change a pixel, if you change the pixel in the center of the image by a value of 1, it's going to affect the output with a higher probability than if you change a pixel by the value of 1 on the very edge of the image, which kind of makes sense, because if you think about the edges, most of the time they contain backgrounds. Most of the time it's not important things that would result in a difference in the classification. So we'll go on to the threat model. Basically, this is the different kind of things that you have to do given the different kinds of knowledge that you have in each attack scenario. The most easy way to attack something is if you have the model hyperparameters. If you're training a neural network, for example, if you know the kinds of tools that were used to train it, the frameworks that were used to train it, each value of the weights in this neural network and the activation function values, the biases, for example. And then if you have slightly less information, you only have access to the architecture. You, for example, know that this is trained with a neural network. It's a 3-layer neural net, for example. And then slightly less data, you have only access to the training data. And even slightly less examples, you have it's basically a black box. So all you have is the ability to input stuff into this classifier, and then you can see the outputs. And we can see that in this case, you can still generate adversarial examples to trick these models. So this is just a study of what people have done in this area. In general, the efforts in adversarial machine learning have been pretty scattered. There's not a lot of new developments, which is why I started talking about this thing, because I feel like the security industry needs to look at machine learning models, since a lot of the critical infrastructure will be shifting to machine learning in the future. For example, self-driving cars, medical devices, and image recognition, speech translation, all of these are powered by machine learning, and sooner or later, we'll be relying on these more than we'd like to. And the thing is that a lot of these are not very reliable. If someone were to go in and try to tamper with such a system, you can find that they can easily be tampered. Some medical imaging devices that try to find, for example, if a cell in a patient is benign or not by looking at the X-ray output, can be easily fooled by something like that. and you can see that there can be dire consequences. There have been examples online and papers published on how deep learning engines used by self-driving cars can be fooled by images that are just held up by a person with a green light, even though there's a red light in real life, but the model just sees the green light or sees a red light with a slight perturbation and thinks that it's not a red light, and then it just proceeds. So you can see how this will result in human loss of life or other dire consequences. And this is why I think that the security industry needs to start to audit these statistical methods, need to start looking at how reliable and how tamper-proof these machine learning models are. So what can you do with limited knowledge? In most real-world systems, we don't actually have access to the model parameters. We don't have access to how the model was actually trained or what input was actually used to this. So a lot of the time, you can make good guesses, and this is kind of a black art. But as you come into contact with more and more systems that are using machine learning, you can make some good guesses. For example, image classifications. The state of the art would be convolutional neural nets. And if you can guess that an image classification is done by convolutional neural net, then you will be able to generate adversarial examples that are more accurate. Speech recognition, they're done using LSTM and recursive neural networks. A lot of the time, anything that has to do with temporal inputs are trained using long short-term memory networks and recursive neural networks. If you're looking at more general purpose machine learning frameworks like Amazon machine learning or any kind of machine learning as a service, then a lot of the time, because they have to generalize well, you're looking at very shallow networks, since having a deeper network will result in more probable overfitting. So that's if you can guess. But what if you can't guess or you're not very sure of the guess? You can still pwn it. So I have a second demo here to show. Captchas are one of the most interesting ways that are most commonly used to differentiate a human from a bot, right? So most websites you go to, if you want to tell that it's a real human there, you would put a captcha there. And obviously there have been many services online like Death by Captcha that you can pay for, maybe a few cents for 1,000 captchas solved to help with your automation. But this is not very scalable because like how many people are willing to sit down at the computer solving captchas all day for $1 a day? So it's not very practical, and it's a matching problem. So excuse me. So there have been solutions out there that use deep learning to solve these things. And so this is an open source example. It's called Captcha Crusher. It's pretty good. I didn't write this. This is just something online, and this is just a tool that I'm using to generate captchas. Pretty generic captchas. They're not the most complicated captchas, but as you can see, the complication, the complexity of the captchas doesn't actually matter. This is what the model actually looks like, and so I won't go into detail explaining the model, but what this is basically doing is to predict the actual is to show the actual labels for this input and then show the prediction. And we're going to show that this actually does solve captchas with a certain degree of accuracy. In most real cases, especially since you don't have access to how the captchas that you're seeing online are actually generated, you can't train a perfect model for solving something like that. So there'll be a high accuracy, but there'll be still things that you get wrong depending on what the captchas look like. Let's generate some captchas here. We generated 10. You can see they look like pretty generic captchas. I think they're pretty complicated, and I might get some of these wrong if I were looking at these and try to type them out. Yeah, just generated more. So I'm deleting them, and I'm gonna show that you can actually generate captchas that trick this model that solves captchas using deep learning. So it's kind of meta, because what we're doing is there's a deep learning model trained to solve these captchas, and we want to generate captchas that can trick this deep learning model so it doesn't successfully solve captchas. So this was the training of the model. You can see training deep learning models are kind of they take a long time, especially if you're looking at a little bit larger images. I started on July 12th at 5:53 a.m. And by the time the model finished, it was July 13th, 9 a.m. So it took took a long time. I did this online on Amazon GPU clusters, so this cost about $120. So it better work well. And let's try it out. And we're evaluating this model from these 10 captures that we just generated, just to see that it made the right decisions. Okay, just gonna wait for it to solve. It's taking some time. This is already pretty fast. I guess it is faster than using like depth by capture or online services with a human behind the computer. Okay, so it predicted all of them correctly. This is lucky. Like if you generate more images, sometimes there'll be like 0.9 accuracy. So let's look at one of them. Let's look at the first one. So the first one, you see IAC-TGB, and the prediction is right. And so let's look at this actual image. It is IAC-TGB. Yeah. So what we're going to do now is to generate the adversarial version of these examples. So they're going to look similar to the original image that this framework can solve very well, but a human is still going to be able to read them correctly, but the deep learning model is not. So we're going to generate these images. These are just the same 10 captures. And what we're doing is we're running it through a substitute deep learning model that I wrote that is different from the original capture framework that is used to solve these things. So this is a substitute model, is an example of a black box. So what this does is just 5 lines of code that generates this. That's in a code base that I'll be releasing online, that I've released online. And so you see, this is the normal example, and this is the adversarial example. They look alike. It's slightly different if you look at the difference. The first one you can't really tell at all, which means that the pixel differences are actually in a white space, and the human eye is pretty bad at differentiating white and slightly off white, so that's probably why. And so if you do an evaluation of the adversarial examples, you see that it doesn't perform nearly as well as with the original examples. And let's just run these. It's going to take a couple minutes. Not a couple minutes, a couple seconds. And so it's going to give me a score at the end. And it's going to show me at each position in this capture, there are six digits in each capture, how many it got right. So let's see, at position 1, it only got 1 out of the 10 right. Position 2 only got 2 out of the 10 right. At position 3, it actually got 7 out of the 10 right. So, but the thing is that with captures, as long as you get 1 out of the 10, 1 out of 6 digits wrong, then you'd be blocked. So we can see that these actually look the same to a human. We'd be able to solve them, but it successfully tricks the deep learning model. So earlier in the presentation, I mentioned something about transferability. Basically, these attacks are not only applicable to deep learning models, they're applicable to all kinds of machine learning models. These are some examples of machine learning models that have been studied. For example, linear classifiers, spectral clustering algorithms, support vector machines, decision trees. The thing is that, and this is still an open research problem as to why this happens, but adversarial samples that are generated using deep learning have a pretty good chance of fooling a previously unseen model, even if it's a totally different model trained using totally different things and in a totally different infrastructure. You can see that this is a matrix of adversarial samples that are generated using one technique and tested on a different machine learning technique. So on the y-axis, you have the adversarial generation method, and on the x-axis, you have the technique that is used to test these adversarial samples. You can see that LR stands for linear regression and SVM stands for support vector machines. If you train a adversarial sample on a logistic regressor and you test it on a support vector machine, which is totally different in terms of infrastructure and the math behind it even, then you see that it has successfully tricks the model with a 91% accuracy, which is pretty good. And deep neural networks are just an easy way of training models since you don't have to meddle with too many model parameters and stuff. And substitute models are another thing that we can use to train adversarial samples on a black box model that we have never seen before. Basically, you want to treat the new model's input with the output labels of the previous model, and you are training a new model based on a model that you don't have access to, which is why it's called a substitute model. And why is this possible? So transferability, as I mentioned before, is still an open research problem. The fact that you can trick machine learning models is because there are many blind spots in the data. When you train a classifier to learn something, it is not learning everything about a dog, or it cannot possibly classify every single image that exists of a dog as a dog correctly, because there are certain blind spots that this model learns. So there's this model versus reality dimensionality mismatch. And people start to question, is this model actually not learning anything meaningful at all? So what this means is that whenever you deploy machine learning models, you should use with caution, especially in critical deployments where there's human life at stake, or when there's large financial loss at stake. You shouldn't make false assumptions about what the model learns, and you should always evaluate how resilient a model is in adversarial in the face of adversarial attacks, and you should spend efforts to make models more robust. So how? The most straightforward one is to basically generate adversarial samples for machine learning models and then train your model using these adversarial samples. Basically, you're trying to iron out any kind of imperfect knowledge. There are other techniques that can be used, like distillation, which means you train the model 2 times, first feeding the original images into the first model, and then you train the second model with the output of the first model, and this helps to distill the amount of information that is stored inside a neural network. This was initially used to reduce model sizes so they can fit on your mobile phone, for example, because if you train it on a large GPU cluster, there will be many dead units that are not actually used in the actual prediction. And you can also use other methods like using loss function and regularization techniques. So deep honing is something that I released at DEF CON this year, and basically it aims to be the Metasploit of machine learning. So what it has is basically some structured code on how you can generate machine learning, generate adversarial samples on machine learning models. And basically, you can input your own machine learning models with their own infrastructure, and then use standard techniques for generating adversarial samples that this framework provides. And it's pretty well documented, I think. There are some links to data sets and papers that are used, and also other sources of code that you can use. So please check it out. Just play around with it, and if you want to help contribute to it, that'll be great. So I think that penetration testing of statistical models and machine learning systems is important because, as I mentioned before, more and more of the time we're relying on these systems, and a lot of people don't have a good understanding of how these things work. So having a good understanding is what's required to really evaluate how resilient these models are to adversarial input. And you should train these models with adversarial samples for increased robustness. So please play with it and contribute. There's this last interesting note that I think is an interesting research area. Deep learning and privacy is an interesting area that has been up and coming in the past few years. Basically, there have been research that's done that shows that you can reconstitute training samples from a trained black box model. So if you can think about a facial recognition engine that recognizes your face and my face, and these models are stored in a mobile phone, for example. Researchers have shown that you can regenerate the faces that are used to train this model pretty easily, just with access to these models, which are distributed to everyone's devices. So can we precisely control the learning objective of these models? Can we train the model without having complete access to training data? These are interesting research questions that I think have to be solved before we can actually rely heavily on machine learning in everyday systems. So this is important because more critical systems rely on it, and we need people with both statistical and security skill sets to develop robust systems and evaluate these infrastructures. So in other words, I think you should learn it. In the next 5 years, it's going to be very important, and that's all I have. Thank you.
Hi, so any questions there?
There. Yeah. So the question is, are there any effective countermeasures that I have found to be effective during the development of machine learning systems? Yeah. So as I mentioned, the adversarial attack vector is only one very particular attack vector against machine learning. There are other like system level vulnerabilities in many machine learning frameworks that affect how accurate the training is done. Previously, I did research in principal component analysis poisoning, which is basically a poisoning during the training phase. So principal component analysis is a technique that's used to select dimensions. It's used for dimensionality reduction. So you run your input through this algorithm, and it will tell you which dimensions can help you make a better classification. And these can be poisoned very easily as well. I think the point behind this is the same as any other kind of system. You have to do some kind of penetration testing because different systems have different objectives, and the attack vectors for each of these systems are different. In some models, it's applicable that adversarial samples should be protected against. For example, if you look at the Gmail malware classifier, which classifies PDF documents for malware. There have been researchers that showed that they can generate malware samples that would actually bypass this, and the prize is that they actually get their samples onto someone else's machine, and it gets past Gmail's malware classifier, which is done using a deep learning model. So the way that you make these better is to basically generate adversarial samples and to train your model with these adversarial samples. And basically, it's like telling a child that you made this mistake in the past, but then I'm going to teach you that this actually is a ship. This is actually a dog, and you shouldn't make the wrong wrong decision again in the future. So that's just one of the ways that can be used, and there are many other.
Okay. Any more questions?
Cool.
Okay. Thank you. Thank you.
Thanks.